Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module Twinning Thermodynamics of Martensitic Transformation, Superelasticity, Mechanism of Shape Memory Effect from the paper Functional Materials. So students, let us see what we are going to learn in this module. First, twinning in shape memory alloys. Second, thermodynamic analysis of Martensitic transformation, including the variation of Gibbs free energy. Third, superelasticity and stress-induced transformations. Fourth, detailed mechanism of shape memory effect. So let us start with a brief introduction about this module. Shape memory alloys, they are known for their excellent memory phenomena accompanied with practical applicability. The special functional properties of SMAs are shape memory effect and superelastic effect. The shape memory effect SME changes with temperature variation and they are mainly attributed to Martensitic phase transformation. Usually, these alloys shows two transformation phases, austenistic at higher temperature and Martensitic at lower temperature. Structurally, martensite forms through a twinning process that is very similar in nature to the deformation twinning. Thermoelastic Martensitic transformation is very sensitive to thermal cycling. There was a scientist, Humbert, who observed that several mechanisms are active during thermal cycling, such as introduction of defects and accommodation of stresses at the grain boundaries. The transformation process gets stabilized due to the irreversible changes in the microscopic state introduced during thermal cycling. Hence, its thermodynamic analysis is very important. Deformation twinning in martensite. Since the twinning is the cause of shape memory effect, basically it occurs in shape memory alloys. So students, it is important to understand and predict the orientation of twins. Twin interface is characterized by mirror geometry where one grain is sheared with respect to the other. This figure shows the important parameters which are related to twinning. Mathematically, a twin is denoted by its elements, and these elements are K1, which is nothing but the twin plane normal, eta1 corresponds to the direction of twin shear. K2 is the second undistorted plane. Eta 2 corresponds to an undistorted vector in the plane K2. S corresponds to the magnitude of twin shear. Now, students, note that in the figure, the open circles and the closed circles represents the lattice points. If a twin is formed, then both the open circle and the closed circles must have the same crystal structure. However, one, that is closed circles, would be sheared with respect to the other, that is open circles. A twin is formed during transformation only when the two variants of the Martensite phase coexist. The twinning operation must allow the original lattice to be restored. Twinning in Martensite. A twin is formed during transformation only when two variants of the Martensite phase they coexist. Original lattice must be restored by this process. Mathematically, two variants denoted by Ij can form a twin only if they satisfy the twinning equation and the symmetry matrix condition. Two solutions exist for the twinning equation, and twinning elements can be found for these solutions. Twin types. So there are two types of twins. Type 1, two lattice vectors lies on the K1 plane and the third lattice vector is parallel to the eta 2 direction. In this case, the K1 and eta 2 are the rational indices, and the two twin crystals, they are related by a mirror symmetry. They are also known as reflection twin. Type 2, two lattice vectors, they lie on the K2 plane and the third lattice vector is parallel to the eta 1 direction. In this case, K2 and eta 1, they are represented by rational indices, while K1 and eta 2, they are irrational. So twins, they are related by pi rotation and hence they are known as rotation twins. So a compound is formed when K1, K2, eta 1, eta 2, they are all rational. Twinning in Martensite. So now students, this table represents the possible number of variants of twins which are possible in some of the Martensitic transformation. So here, as you can see, there is a particular transition, that is, consider the example of a transition from cubic to tetragonal. A twin type is compound and the number are 24, and these are the observed elements or the materials which shows this type of transition. Thermodynamics of Martensitic transformation, or MT. Martensitic transformation is defined by four important temperatures which have been explained earlier also, and these are MS, MF, AS and AF. These transformation temperatures can be determined by measuring some physical properties. So, as you can see in this figure, so students note over here that this shows the variation of the physical properties to determine the characteristics temperature of Martensitic transformation. So this shows the resistance ratio and the change in the slope provides the information about the characteristic temperature. Another important thing to note in this figure is that one material, that is copper cadmium, has a very small transformation zone around 15 Kelvin, while the other material, that is iron nickel, has a very large transformation zone, approximately 400 Kelvin. As discussed earlier, when the transformation zone is small, driving force is also small, and hence the process is reversible, which is also called as the thermoelastic. On the other hand, when the transformation zone is large, driving force is large, and the process is no longer reversible. So these processes are called as non-thermoelastic. In effect of SE and SME can be found only in thermoelastic transformations. Thermodynamics of MT. So we are continuing with the discussion over thermodynamics of Martensitic transformation. So students, to represent the thermodynamic equilibrium temperature between the two phases, the Gibbs free energy is an important parameter. So Gibbs free energy of the two phases are being shown in this figure. The plot for the two phases intersect at the temperature of T0, where T0 can be said as the temperature at which the two phases are in thermal equilibrium. So, however, this equilibrium temperature T0 cannot be measured directly. So, as you can see from this figure, here GC, basically this delta GC is the chemical energy term, delta GS is the surface energy term, delta GE is the elastic energy term, and delta GNC is the non-chemical energy term. So all these terms are summed together to give the total Gibbs free energy of a system when the Martensitic transformation takes place. That is, we can write delta G to be equal to delta GC plus delta GS plus delta GE. We can write delta GS plus delta GE to be equal to delta GNC, where delta GNC is of the same order as that of delta GC. Thus, a nucleation and the growth kind of process is required for the transformation to proceed. Once the nucleation of Martensite phase takes place, then in the parent phase during cooling, then it can grow only when the circumstances are right, meaning only when the driving force, that is the temperature difference, is larger than the elastic energy around the nucleated Martensite phase. Hence, a critical supercooling is required, which is delta Ts, and similarly a critical superheating, that is delta Ts, is necessary before the parent phase can nucleate and start to throw back. Some rationale can be applied to MF temperature, since the growth will always occur only to the extent that driving force equilibrates with the elastic energy around Martensite. Hence, the transformation will go to the completion at even further supercooling, and hence MF is less than MS. Thus, the transformation is only temperature dependent and not the time dependent. Stress temperature phase diagram. Now, with respect to the phase diagrams, one may consider, or we can see or talk about a different kind of phase diagram for Martensitic transformation. It is the stress temperature phase diagram. Since the Martensite interacts with the stress field, application of stress is bound to have an influence on the characteristic temperature of Martensitic transformation. This is shown schematically in this figure, and here, as you can see, that the stress temperature phase diagram shows that how the stress is related to the temperature, which is associated with shape memory alloys. So students, note over here that the x-axis shows the usual transformations associated with the temperature. However, the y-axis represents the effect of stress on these transformations. It also hints at the formation of stress-induced Martensite, where Martensite can be produced only by applying stress and without changing temperature. Superelasticity. Superelasticity of pseudoelasticity is an effect which is usually associated with shape memory alloys. So students, here we will be discussing about the superelasticity. So this figure which is shown over here shows the schematic of the evolution of microstructure with increasing and decreasing load, where the light color is the austenite and the grey color is the martensite. Correspondingly, the load displacement curve is also shown over here, as can be seen if we start with a completely austenitic microstructure and start to apply stress. Then Martensitic transformation starts to takes place, and this is nothing but the stress induced Martensite. So once the transformation is completed to Martensite and the load is removed, the strain is seen to drop. Concomitantly, this microstructure is found to see the transformation from martensite to austenite. In fact, upon the complete removal of the load, total strain is reversed and original microstructure is restored. So here we observe the two important phenomena. First is stress-induced martensite transformation. That is, martensite was found to form with the application of load and without changing temperature. Second is superelasticity. Strain which was induced because of transformation to martensite is seen to be completely recoverable when the load is removed. This elasticity seen because of recoverable strain transformation is called as superelasticity. Superelasticity. A schematic stress-strain plot is shown in this figure for copper, aluminium, nickel alloy. Here again we see the superelasticity effect in the single crystal alloy. In this particular material, strain up to 8.5% was found to be recoverable upon loading. So what will happen when we keep loading the material even after complete transformation into martensite phase has taken place? The answer is this plot. The sharp rise in the stress at strains above 8.5%, that is the top right end of the plot, leads to the slipping instead of martensitic transformation, and hence permanent deformation begins to set in. This implies that these strains will not be recovered. The above plot was obviously obtained at temperatures where austenite exists, that is T greater than ms. In fact, in practical applications, the temperature needs to be sufficiently above AF to observe complete strain recovery upon unloading. SMA and superelasticity. So now, students, the question arises that how does this plot change when the temperature is changed? The answer to this question is this plot. At intermediate temperature, that is slightly above AF, superelasticity or SE or pseudoelasticity is observed as seen in the curve C. At very low temperature, and the curve corresponds to B, that is T2 is less than ms, martensite already exists in the microstructure. However, such systems can still accommodate some strains by allowing one variant of the twin to grow at the expense of all other variants. If the load is removed after partial or complete transformation to one variant of martensite, then the strain does not go away automatically. However, the strain does go back to zero upon heating. At microstructure level, upon heating, one or many variants of martensite transform back to the parent phase and hence the strain is recovered. At very high temperature, which corresponds to the curve A, loading does not result in any phase transformation and the material shows the usual stress-strain plot with usual work hardening. This is a critical temperature termed as MD, above which the superelasticity behavior is lost and the material behaves like the usual structural material. SMAs and superelasticity SE. When copper zinc tin alloy single crystal is tensile tested at temperature below AF, strains are permanent, but they recover after heating above AF. This is SMA. When tested at temperature above AF, strains recover by unloading. This is SE. Thermodynamic equation shows that higher elastic energy favors MT. Stress-induced Martensitic transformation or SIM. So we are again continuing with the discussion over shape memory alloys and superelasticity. Similar behavior is observed for copper zinc tin alloy, and this schematic or the stress strain behavior for this alloy is shown in this figure. Note that for this material, MF is 208 Kelvin, MS is 221 Kelvin, AS is 223 Kelvin, and AF is 235 Kelvin. So in this plot, the solid lines shows the stress strain behavior on loading and unloading, whereas the dashed lines shows the strain path upon heating at temperature above AF. Here again we see two distinct behavior at temperature below MF and at temperature above MF. At temperature below MF and also for the temperature below AF, as long as the starting material is in Martensite phase, we see that upon loading, basically unloading, the total strain is not recovered. However, when the sample was heated above the temperature AF, the total strain was recovered. This behavior leads to the shape memory effect. So, on the other hand, when the samples were tested above AF, that is, when the microstructure was completely parent phase, one observed almost complete recovery of strain. So what is more interesting is that the elastic behavior is not linear and hence very large strains are also recovered. As stated earlier, this behavior is due to the transition from the parent phase to the Martensite phase and upon loading, and then the reverse transformation from the Martensite phase to the parent phase. This behavior leads to superelasticity. Orientation dependence. Twins, they have crystallographic geometry and hence some will be preferred under certain loading directions while others will be preferred under other loading directions. Superelastic strain for a particular orientation corresponds to the plateau length in the stress-strain curve. Transformation strain for different orientations can be calculated from Bain strain model and it shows strong orientation dependence. Orientation dependence. Strain that can be accommodated according to the Bain's model will be different in different directions upon Martensitic transformation. So this translates to varying amount of superelasticity strain possible for different orientations. So this is shown in this figure for copper, aluminium, nickel single crystal, where the orientation dependence of the stress-strain curves for this alloy have been represented. And the another figure on the right shows the schematic of the orientation dependence transformation strain for copper, aluminium, nickel alloy single crystal. Stress-induced transformations. Martensitic transformation proceeds by a shear-like mechanism and thus it interacts with the applied stress. Shear stress always assists in transformation, but a normal stress may assist or opposite depending on various factors including volume change, sign of stress. Hence, effect of stress may be completely different in two different materials. For example, hydrostatic pressure aids the transformation for gold cadmium while it opposes for iron nickel alloy. Thermodynamics governs that Martensitic transformation can also take place by the application of stress. So, the transformation from the parent phase to the Martensitic phase on application of stress depends upon the temperature also. So, the structure of various phases can be determined by neutron diffraction. As much as 18% of superelastic strain can be obtained. Stress-induced transformations. So this figure shows another example of stress-induced transformation. Here stress was applied to copper, aluminium, nickel alloy single crystal. At a particular stress, the transformation begins from gamma 1 prime to beta 1 double prime, and this is the evident by the change in the slope of the stress strain plot at this critical point. This system is interesting because beta 1 double prime is an intermediate Martensitic structure and the final structure is alpha 1 prime. When microstructure gets completely transformed to beta 1 double prime, then further loading causes the transformation to alpha 1 prime. Thus, in this system, we see two transformation and two critical stress values. Now, let us discuss the mechanism of shape memory effect, that is SME. So, till now, we have discussed or we are in a position to revisit the stress temperature phase diagram for shape memory alloys. We can even draw the transformation path which depicts the various properties, that is SME, SE, SIM, and these have been shown in this figure, which shows the stress temperature phase diagram for shape memory alloys, showing the transformation during the shape memory effect. So students, note from this figure that on going from A to B, parent phase gets completely transformed to Martensite phase. During this transformation, many variants of Martensite may nucleate and grow. However, on going from B to C, upon loading or applying stress, one variant of Martensite will dominate and consume all other variants. Upon unloading, there will be no change in the microstructure and hence no change in the strain. However, on going from D to E, the temperature is increased to the level where martensite is not stable and only parent phase can exist. Since the parent phase has higher symmetry, it has only one variant, and hence all the changes in the shape given during B to C is regained as the structure and microstructure come back to the starting point. This transformation path shows the changes and also details the mechanism following the shape memory effect. So the bottom line is that since the parent phase has only one variant and the martensite phase has several variants, we see shape memory effect, SMA, and superelasticity. This stress temperature transformation, or we can say it also involves the straining of the material, and hence a more complete picture is obtained when we add another axis for the strain. This is clearly shown in this figure. So this figure shows the transformation from a different point of view. When we cool from the parent phase to below the MF temperature, we obtain several variants of martensite which are related to each other by twinning. Upon loading, one variant dominates and starts to consume other variants until complete detwinning occurs, and it has been shown in the figure clearly. So, at this point, if the load is removed, no micro or macro structural changes takes place. However, there is a permanent strain remaining in the material. Upon heating from this stage, the strain reduces along with the transformation from martensite to parent phase, which is also very easy to understand using this figure. So, in the previous discussion, the transformation very clearly in terms of stress, strain, and temperature changes have been discussed. The mechanism. This figure shows the schematic of a long rod going through various microstructural changes and exhibiting the shape memory effect in the process. The above figure shows the rod at high temperature phase in A when it has been given a definite shape, that is A rod in this case. Upon cooling to low temperature, the phase and hence the lattice structure changes. In order to keep the overall shape the same, the material forms several twins as shown in B. When some additional stress is applied, one of the twins which is favored by this stress starts to grow at the expense of the other. This has been shown in figure C. twin boundaries move so as to accommodate the applied stress. So one can only apply stress large enough to create one single variant of Martensite phase in the rod. The rod can be heated back at any stage up to this critical deformation, and all the variants turn to the parent phase. Since the parent phase has higher symmetry, it has only one variant, and hence, although the deformed shape can have multiple shapes depending on the combination of various Martensite variants. The high temperature parent phase has only one shape, and it will be the shape given to it at high temperature. This has been shown in figure D. Upon cooling again, the material will change back to Martensite phase with self-accommodated twins, so that overall the shape does not change. So students, this figure, that is the figure shown over here, shows another example of a one-way shape memory effect, which is showing changes at micro and macro levels during transformation. So the figure A shows the change of the transformation to the Martensite phase. It is again cooled and then deformed, and then it is heated to regain its original shape. So part A corresponds to the temperature greater than AF, B when the temperature is less than MS, and C when temperature is greater than MF. So students, let us summarize what we have learned in this module. First, deformation twinning in Martensite phase along with its types has been discussed. Thermodynamical analysis of Martensite transformation, including the variation of Gibbs free energy for parent and Martensite phase, has been done. Third, superelastic behavior and shape memory effect in copper aluminium nickel alloy single crystal has been explained along with orientation relationships. Fourth, detailed mechanism of one-way shape memory effect is discussed, showing changes at micro and macro levels during transformation. Thank you.